To reintroduce myself, my name is. My name is H to the OP.
Logic gates are the building blocks of all digital electronics and computers. Today, we will show you how to make AND, OR, and NOT gates using a breadboard, ICs, and LEDs. Breadboard, used to build circuits without soldering. It lets you easily connect components and rearrange the circuit as needed. 7408 AND gate IC. This chip contains AND logic gates. It outputs 1 only if both inputs are 1, helping demonstrate AND logic operations. 7404 NOT gate IC. This IC contains inverters, not gates. It flips the input signal if the input is 1. The output becomes 0 and vice versa. 7432 OR gate IC. This chip contains OR logic gates. It outputs 1 if at least 1 in input is 1, showing how OR logic works in circuits. LEDs. LEDs are used to show the output state of your logic circuit. They light up when the output is high. Resistors 220 or 230. These resistors limit the current going to the LEDs to prevent them from burning out. Jumper wires used to connect components on the breadboard, linking the IC's power supply, LEDs, and other parts. Power supply 9 volts battery and connector provides electrical power to the entire circuit so all components can operate.
The 7408 integrated circuit was placed at the center of the breadboard, so its pins were separated across the middle gap. This activity aimed to build a simple AND gate circuit using the 7408 IC, jumper wires, a 220 OHM resistor, a red LED, and a 9-volt battery. The goal was to show that an AND gate only produces a high output when both inputs are high. Because the 7408 operates at 5 volts, the 9-volt battery was first connected to a 7805 voltage regulator to reduce the voltage to a stable 5 volt. The regulator's output was connected to the breadboard's positive rail while the ground was connected to the negative rail. This ensured that the IC received the correct voltage.
First, place the IC in the center of the breadboard sitting across the middle gap. This separates the left and right pins so they don't connect accidentally. Make sure the nut is at the top so you can identify pin 1 correctly. Next, connect the yellow jumper wires. These wires are used as the inputs going into the IC. They are placed on the same rows as the input pins so you can give the gate a high or low signal. Then, attach the blue wire. This wire comes from the output pin of the IC and goes to the side of the breadboard where the LED is connected. The blue wire carries the logic output, which determines whether the LED will turn on or off. Now, connect the green wire. It connects the IC pin to the ground. Then, place the LED on the breadboard. The longer leg should connect toward the output side. The shorter leg should be placed toward the resistor. Then, connect the resistor from the shorter leg of the LED to the ground rail. This protects the LED from too much current and prevents damage. Finally, attach the 9B battery connector. Red wire is for the positive rail and the black wire is for the negative rail. Then connect the 9B battery. This gives power to the entire circuit so the logic gate and LED can function.
In this project, the OR gate integrated circuit was first positioned at the center of the breadboard to ensure that each pin was properly separated and accessible for wiring. Following this, the power connections were established by linking pin 14 to 5V supply and pin 7 to the ground rail, thereby providing the necessary operating voltage for the internal logic components of the IC. The inputs were then assigned by selecting one OR gate within the chip, designating pin 1 as input A, pin 2 as input B, and pin 3 as the output. Two jumper wires served as input selectors, allowing each input to be manually set to either a high state by connecting to the 5V line or a low state by connecting to ground. To visualize the output response, pin 3 was connected to 220 OHM resistor, which then led to the anode of an LED, while the LED's cathode was connected to the ground. Through this configuration, the LED illuminated whenever the OR gate produced a high output by applying various input combinations and observing the LED's behavior. The experiment successfully demonstrates that an OR gate outputs a high signal whenever at least one of its inputs is high, highlighting the fundamental operation of digital logic in electronic systems.
In row 1, both inputs are low. An AND gate needs both inputs high to produce a high output. Since both inputs are low, the output is 0. LED stays off. In row 2, input A is low, but input B is high. In an AND gate, even if one input is low, the output will still be low. So the output is 0. LED stays off. In row 3, input A is high, but input B is low. Again, because both inputs must be high, the output becomes low. So the output is 0. LED stays off. In row 4, both inputs are high. This satisfies the condition of the AND gate. All inputs high result in high output. Therefore, the output is 1. LED turns on.
During testing, the green wire is the input wire. So as you can see in our truth table, our first input is 0 and output is 1. So when you place the green wire on the 0, and the NOT gate inverts the signal. This makes the output 1, so the LED turns on. Then our second input is 1 and our output is 0. So when you move the green wire to 1, the NOT gate flips the signal to 0, so the LED turns off.
In row 1, both inputs are 0. An OR gate needs at least one input to be 1. No high input means the output is 0. LED off. In row 2, input A is 0 but input B is 1. Since one input is high, the OR gate outputs 1. LED on. In row 3, input A is 1 but input B is 0. There is a high input, so their OR gate outputs 1. LED on. In row 4, both inputs are 1, at least one is high, so the output is 1. LED on.
Hold up. Wait a minute.